Week 4 starts to get into the nitty-gritty about weather. When we start talking in Chapter 7 about atmospheric circulations, we are now building upon material we have learned previously. Specifically, we've talked about how air responds to pressure differences. So air moves from high pressure to low pressure. But those pressure differences are actually generated by temperature differences. It's interesting that the temperature distributions actually are what create wind, because the temperature differences cause the pressure differences. So Chapter 7 discusses that in great detail. One of the fundamental concepts I brought up earlier in an earlier video is that this applies on all scales. So small scale, medium scale, large scale. These temperature variations are what causes the wind to blow, and then the wind circulations of Earth. So on the small scale, you're talking maybe the beach versus the ocean. So a couple hundred meters to maybe a mile. That temperature difference causes the wind to blow along the coast. Then there are the medium scale, where you might be talking about the Tibetan Plateau heating up, or maybe the Great Basin of North America heating up. Those areas heat up warmer than the area of the same size near it, and that causes the wind to blow towards that area, and you get what are called monsoons. So the southwestern part of the United States actually has a monsoon in late summer because the Great Basin warms up. So that's the medium scale. On the large scale, the global scale, the difference in temperature between the poles and the equator, it causes the jet stream and causes the wind to blow. And I talked about that in a previous video as well. So these temperature variations cause the pressure variations, and that can happen, and that causes the wind to blow, and that can happen at any scale. And that is what the chapter is in a nutshell. A couple of other finer points. There is something called the ITCZ. That's the Intertropical Convergence Zone. The Intertropical Convergence Zone, or the ITCZ, is normally over the equator. It oscillates north and south depending upon the season. It's always where the warmest air is. It is there because both hemispheres have air rushing towards the equator, and air, when it's rushing towards it, can't just pile up on top of each other. It has to go somewhere, so it goes up. The intertropical convergence zone, the air is converging, and then it's forced to rise. That causes actually a thin strip of thunderstorms to actually, at times, encircle the entire Earth, at least where the sun is shining. You'll see this nice little thin strip of thunderstorms. So it's really cool that you can actually see the general circulation of Earth happening, and this rising motion over the equator. What goes up must come back down, of course, so all that rising air near the equator in the ITCZ reaches the tropopause, spreads out north and south away from the equator, and then comes back down. And that subsidence, that sinking air, erodes all cloud material, so it's bright and sunny and very dry. And it just so happens this is where the major deserts of the Earth are located. And right about 30 degrees north and 30 degrees south, you'll find out that most of the major deserts, like the Sahara, that's where they exist. And that's why they exist, is because the general circulation of Earth causes the air to subside at those latitudes. So those are just a couple things we'll be learning about this week. You may have noticed storms to your west eventually travel towards your area. Maybe you've noticed that weather phenomena happening in California maybe gets to your day, gets to you in Missouri, a couple of days later. So the weather generally travels from west to east. Why is that the case? Well, that is because the winds of the atmosphere generally travel from west to east also. So it basically just pushes whatever is to the west towards the east. Why do the winds blow typically from west to east, at least over the United States? At those latitudes, why is the wind blowing from west to east? The reason is because, think back to that slinky example, the pressure, or the atmosphere is less dense near the equator and more dense near the North Pole. Think back to those slinkies. At the same elevation above the ground, the pressure is always higher near the equator than it is near the poles. This causes air to rush from high pressure to low pressure, which causes the wind to blow. Great, except that the Earth is now rotating. In the northern hemisphere, Earth's rotation causes the wind to turn towards the right. Well, if you imagine a plane or the wind traveling from the equator towards the North Pole and then it turns towards the right, it's suddenly traveling east. That means that the air is now instead of traveling from straight south to north, is now traveling east. So that means, this is we define wind by where it comes from. We have westerly winds. That is why the westerlies exist across the United States. That's why weather travels from west to east. So we have these wind patterns set up because of the temperature variations, because those temperature variations are causing pressure variations. So those pressure differences cause the wind to blow, and in a global sense, those are pretty well permanent, that they stay put. The only thing we haven't considered is that the Earth is actually rotating while these pressure differences are in place, which causes the wind to actually turn. In the northern hemisphere, it turns towards the right, and in the southern hemisphere, it turns towards the left. This causes high pressure in the northern hemisphere to appear to rotate clockwise, and low pressure in the northern hemisphere to rotate in a counterclockwise fashion. This is important because it affects ocean currents. And then in extension of that, the climate system of the Earth. So for instance, high pressure is over the Atlantic Ocean most of the time. This because the eastern United States is on the western side of that high pressure, it gets southerly flow, and that brings up warmer waters along the east coast. On the west coast of North America, near California, that is on the eastern side of the Pacific high pressure, and that causes northerly flow, which causes ocean currents to actually follow that wind. There's the important thing, is that the ocean currents are going to follow those wind patterns as well. So in California, it's actually bringing down current from the north, and since that area is colder, the current is usually colder as well. There's also something called upwelling. When winds follow the coast, it drags some of that water with it. So wind is the main driver of ocean currents. But Coriolis force works on any fluid. We consider the atmosphere a fluid, but of course the ocean, the water, is a fluid too. So when the water starts moving, the Coriolis force, or the rotation of Earth, works on that as well. And because in the case of California, it's coming from the north, turn that water that's flowing from the north to the right, and it causes it to move away from the shore of California. The ocean isn't going to make a big cavity, so water from below upwells or comes up towards the surface, and that causes the ocean waters off of California to be quite cold. The interplay between the atmospheric circulation and the ocean currents becomes very important in terms of the climate system. In the Pacific Ocean, for example, the winds near the equator are almost always coming from the east, so from South America towards Indonesia. That promotes water being pushed towards Indonesia. At the same time, the area over Indonesia has really, really warm water, and that actually causes a lot of convection, or storms, to form in that area. And that area is called the chimney of the world because so much convection happens there. It vents the air from near the surface up to the tropopause and then spreads it back out. So it's very much like a chimney of the world. When the winds that are blowing from South America towards Indonesia change, that chimney of the world changes, and that actually changes the atmospheric circulation of the entire globe. What I just described in a microcosm is ENSO, or El Nino and La Nina. When the wind, basically we don't quite understand everything how this happens. It's a very complex system. But one of the ways that this works is the winds are always blowing from South America towards Indonesia near the equator. Eventually this can pile up some water near Indonesia, and just like if you were to take a hairdryer into a bathtub and start blowing water towards one direction, it eventually just piles up, and it really can't pile up too much more, and eventually that water will slosh back. In that sloshing back process, that's when you can get the climate system, or the atmosphere, to switch from an El Nino to a La Nina. And that's when the chimney of the world is altered, and that's why the climate, or the weather where you're at, may be significantly altered depending on if it's El Nino or La Nina. So interesting how the interplay of those work very hand in hand. And so understanding that as you read Chapter 7 will really help you understand ENSO.